Okay, MCT4C day 39, lesson 4.5, logarithms, day 2. Last day we were introduced to logarithms and we were solving problems like in the 3-minute review here. And there was a couple of ways that we thought about them. I'm going to sort of do the old way first, where we thought of that as a value and then we change it to our exponential form, where I see that the base is 2, and the exponent is x, and then I'd figure out how to solve that. And in fact, that's the way we think of logarithms is the exponent. What exponent, base 2, would give me an answer of 32? And in fact, that's the easy way we think about doing this, is we say, okay, for this to work out, this has got to be 2 to the exponent something. Oh, it's 2 to the exponent 5. And it's kind of like the logarithm and the exponential function wipe each other out. And I'm left with just the exponent 5. In this one, same sort of thing, almost the same question actually, except for this is 2 to the exponent 4. The logarithm and the exponential function, since they're the same base, wipe each other out. Whoops, and I'm left with just the exponent 4. Here, we've kind of got our work done for us, because we said we wanted to write this inside thing as a power of the base, and it already is. Well, what's the exponent then? Just 1. This answer is 1. Now this one's weird, because I'm thinking, okay, how do I get an answer of 1 when the base is 3? What exponent would give me an answer of 1? Well, remember, anything to the exponent 0 is 1, so this answer is 1. There's some things that we can do. What's some things that we can't? Well, notice, we can't take the log base anything of just anything, right? 32 and 16 and 5, all these were fine because we could write the number inside this power as 2 to the exponent something. But here, I can't. I don't know what this is. I know that it's somewhere between 2 and 3, but I don't really know it. And even if I change this to the old style, call that x, and then I got 2 to the exponent x, this equation, we were having trouble solving it too. We were using our graphing calculator to the intersect feature, and we were using what's it called? Guess and check on our scientific calculator, and we're stumped here. There should be a way to do these things quickly on our calculator, and this is something that we're hopefully going to resolve today. So solving problems using logarithms. Observations from last day. Well, from last day, we saw that when we have a logarithm that meets up with the exponential function of the same base, they kind of wipe each other out, and I'm just left with the exponent, just x. And the reason was, work over here somewhere, that if I have a function and the inverse of that function bashing up against each other, they kind of annihilate each other, right? When I add 3 and subtract 3, well, I'm just left with whatever the input is, and that's the idea. And this one was a special case where a was to the exponent 1, this is to the exponent 1, and this was that special case where we have log base, well, that's a to the exponent 0. Those cancel each other out, and I'm left with an exponent of 0. Also note that these are 2 from the 3-minute review. This was 5. This was 4, and if I added those together, if I wanted to, I'd get 9. Well, look at this. If I thought of what 32 times 16 is, that's 512, and that's actually a power of 2 as well. That's 2 to the exponent, yep, you got it, 9. Those things annihilate each other, and I get 9. So therefore, I can say the log base 2 of 32 plus the log base 2 of 16 is the log base 2 of 32 times 16. So when I have two logs and I'm adding them, I multiply the powers on the inside. This is our first of a few more, what I like to call log laws, laws of logarithms. For instance, this is the one here in general where it's base A. When I've got two logarithms and I'm adding them, I multiply the powers on the inside, like this. Over here, when I'm subtracting them, I divide the powers. Well, why does that make sense? Well, we'll talk about this in a second, but these are the log laws. Here, we kind of saw this one because it's kind of like log base A and something to the exponent something. It's like we're left with only this exponent. Well, that's when it was log base A of A, and this wiped each other out, but it's not log base A of A. And in fact, that's not 1, so I could think of it as n times log base A of m. Okay? And where this makes sense, or where we've seen this before, is our exponent laws. Like we have these exponent laws, and I'll write them down real quick. You don't have to if you don't want to. We got, if we're multiplying two powers, we know we added the exponents, right? And if we had two powers and we were dividing them, we subtract the exponents. These are all rules that we knew from grade 10 or so. And if I had powers of powers, exponents on exponents, I multiply the powers, right? A and m. Well, have a look. Remember, a log is an exponent, right? So let me read these two things in two different ways. When I'm adding logs, I'm multiplying the things on the inside. When I'm adding exponents, I'm multiplying the powers. Adding exponents, multiplying the powers. It's the same thing. When I'm subtracting the logs, I'm subtracting the exponents. That means I must be dividing the powers. M and n are the powers here. When I have exponents on exponents, I multiply the. When I have exponents on exponents, I have powers of powers. Then I multiply the power. So these statements are analogous. They're exactly the same thing, written in a slightly different way. And we're not going to prove any of these. We're just going to use them. And so off we go. Here we go. Here's the first one. We've got two powers at the same base, and so they're added. So that means I can multiply them on the inside. Well, why is that so awesome? Well, 3.2 times 10 is 32, and then this I can do using the stuff we did yesterday, right? This is 2 to the exponent 5, and that's just 5. Notice I don't know how to do this, and I don't know how to do this separate. I can't write, for instance, log base 2 of 2 to the something and get 10. But if I use a log law, this was easy. B. Notice here I've got two logs at the same base and I'm subtracting them. So that means it's divide on the inside. This one I can't, can't get in on the action here because it's a different base. Just like if I had different bases on my exponent rules, I had to do them separately. Well, how am I going to handle this? Well, I need to be able to write 2 as 8 to the exponent something. Well, we've pulled this trick before, right? 8 to the exponent something is equal to 2. Well, this is 2 to the exponent 3, and I can see that 3x equals 1, x is a third, and you might have recognized that right away and just written that down. That's the exponent 3. Then now I've got this idea of a log and an exponent. All I'm left with is the 1/3. Here, 50 divided by 10 is 5. I can see that's 1. But over here I've got 1/3 log base 8 of 8. That cancels each other out. Then I got 1 plus a third, 1 1/3, no calculators necessary. Here, this one, it kind of looks like this one, right? Right? And we said that that's equal to, I could, if I wanted to, think of it this way, right? Where the number in front gets written up here. I'm going to pull that trick. Just because this number is some big number. What is it? It's 256. Now, can I write 256 as 4 to the exponent something? Yeah, that's 4 to the exponent 4. 16 times 16. And so there I've got a log base 4 and an exponential function base 4. They wipe each other out, and I'm left with just plain old 4. No calculator. Nice. All right, how far along am I? Yeah, I'm going to stop there and go to part 2 in just a